We'd already talked about equilibrium, and our old idea of equilibrium we now refer to as translational equilibrium, which is just another name for linear. In translational equilibrium, what we have is that the forces balance out. That means, equation-wise, that the total force is going to be zero. All the up forces equal the down forces, and all the force to the left bounce out the ones to the right. How do we know if we are in translational equilibrium, though? Well, we know we're in translational equilibrium if there is no acceleration. In other words, we want to look for things like it is not moving, or it's moving at a constant velocity. So it can be moving and still be in equilibrium as long as it's moving at a constant velocity. So those are some terms that you want to look for. Now what we're going to do is take the same ideas and apply it to rotation. In rotation, we're not talking about forces. Instead, we are talking about torques. And so the torques are balanced. So the torques that are clockwise bounce out the ones that are counterclockwise. And so the total force, the total torque adds up to zero in terms of rotational equilibrium. Now, it still means that there's no acceleration. But in this case, because it's rotating, we say there's no angular acceleration. That's your alpha. So there's no angular acceleration. So how do we know if there's no angular acceleration? So just like before, it is either not moving, or it is moving at a constant angular velocity. Which is your omega. So again, it can be moving and still be in rotational equilibrium as long as it's moving at a constant angular velocity.